How's that? Is that all right? Okay, thanks very much, Christo, and thanks everybody for the great hospitality being shown to my team and I. So I'm Matthew Bailes, and I love to work on neutron stars. Might just need to turn it down a little bit, if the can turn down the volume down a bit.
A little bit down.
No? Excellent. The inverse square law in that machine. You should do physics. Okay, that's a bit of getting my own here. Right, so I'm going to talk to you about how we use the MeerKAT telescope, which is in South Africa, to explore theories of gravity that Einstein popularized and made famous. We're going to start off just looking at the stars in the night sky. So in the night sky you can see about 6,000 individual stars with the naked eye. And the positions of those stars have all now been determined by the Gaia telescope, which is this amazing European mission. There's actually two telescopes that look in 90 degrees apart, and they rotate around the sky, and they measure the angle between stars incredibly accurately. And by the fact that the Earth goes around the Sun, it actually changes the angles between all the stars in a very subtle way. And we call that parallax. So if I'm looking at a star compared to the fixed background, and my head is the Earth going around the Sun, the apparent position changes. And so they've been able to use that to determine the positions to all of the 6,000 stars you can see with your eyes. Some of them are actually too bright for Gaia, and they had to use the precursor telescope Argos. But these were all the stars you can see with your naked eye. And we'll just zoom out a little bit. They form this nice cloud. And the actual distance to the center of our Milky Way galaxy is shown by that blue dot. So our stars are actually quite local to the Sun. Most of the ones you can see are within about 1,000 parsecs, it's about 3,000 light years. The distance to that blue dot is about 8,000 parsecs, or 25,000 light years. And so it would take light 25,000 years to reach the center of the galaxy. And you can see that most of the stars we can see with our eyes are actually quite close. Some of the brightest ones are actually the furthest, and they're the supergiants that are giving off more than 1 million times the light of our Sun. So we'll just go talk. And before I start, I just want to thank my colleagues, Ryan, Matt, Nick, Daniel, and Marissa, who are helping us run the workshop here for the undergraduates, postgraduates, and staff members. But I'm paid for by the ARC Centre of Excellence for Gravitational Wave Discovery in Australia, and they fund our research into gravity. And we actually have 6 universities in Australia that are all studying gravity under our leadership, and we're actually searching for gravitational waves. We use these things called pulsars, which are rotating neutron stars, to aid in our studies. And in this talk, I'm going to teach you a bit about how these stars are made, how big they are, how fast they rotate, and all the interesting things you can do with them. So this is the MeerKAT. This is a 64-dish radio telescope north of Cape Town, a few hundred kilometres. It's in a kind of very dry part of South Africa. I think it's about 1 kilometre above sea level. And these 64 dishes usually all look in the same direction at the same time. Radio waves from the heavens come in, they bounce off the dish, they bounce off the secondary reflector and then into a feed. And that stimulates a voltage. We amplify that voltage and we digitize it over 1 billion times a second. And then over optical fibers, all that signals are sent to a massive computer. And the data is combined, what we call coherently, so all the radio waves are lined up and are what we call in phase. And then we send that to a little computer that we send over from Australia called PTUs. And that takes the data and observes neutron stars. But MeerKAT can do a lot of amazing things. So this is an image it made in radio waves of the center of our galaxy. And when you normally look at the center of the galaxy, it's shrouded in dust and difficult to see, but the radio waves go straight past the dust. And you can see all these amazing things. So we have, these things are called supernova remnants. So that used to be a very large star that blew up, and the shell of material is expanding. Sometimes in these supernova remnants, there's actually a neutron star that's left over. And there's other objects in here, like these strange filaments that we don't really know how they occur, but we just wave our hands and say magnetic fields and stuff like that. And then right at the center of our galaxy, there's actually a supermassive black hole. And that black hole weighs 4 million times as much as the sun. And people who have studied the stars going around that won the Nobel Prize for Physics just a few years ago. There's also, if you look in the background, I'm not sure exactly where to look, but there's actually other supermassive black holes in other galaxies that are squirting out jets in this image, but I'm not sure where to point, so I don't want to make a mistake. MeerKAT's also looked at the gas that is in our universe, and these blobs here are actually not stars, they're galaxies. Each one consists of about 100 billion stars, and they sometimes form in clusters, and they squirt out these jets of emission. And the reason they're squirting out the jet is that there's a supermassive black hole in the center of these galaxies, accreting material, and it causes the material to rotate near the speed of light. The material gets ionized, so it generates these intense magnetic fields, and that powers these amazing jets of emission. And these things are millions of light years in extent. So let's go back to the Earth, which is something we're very familiar with. And the Earth actually defined a meter. So the French decided that there should be 10 million meters from the North Pole to the equator. And so they paid somebody to pace out 9 degrees of latitude, and they said that's 1 million meters. And so that was the original definition of a meter. So this means that the Earth's radius is 6,380 kilometers. That's just 40,000 divided by 2 pi. And the mass of the Earth is about 6 by 10 to the 24 kilograms. This means the density of the Earth is about 5.5 grams per cubic centimetre. Water is only 1 gram per cubic centimetre. That's why the water floats. And it's what's called a rocky planet. And the acceleration due to gravity is just Newton's constant times the mass of the Earth divided by the radius squared, and that comes out to 9.8 meters per second squared. We often call that G. If you experience more than a few G, you black out. So if you get to 10 G or something, then you lose consciousness. So, unfortunately, in my talk, I do a lot of lying when it comes to scales. Otherwise, the universe is very, very boring. So this is our sun, and if I had to show you the Earth to scale, it doesn't actually fit on this plot. So I can turn on a trail and fly overhead, and I have to zoom out a long, long way before we start seeing the Earth. So that's where the Earth is, that little trail over here. And you can see the sun has become this pathetic little dot. So in my talk, I'm going to have lots of stars going around each other and so on. But if I made them all with proper scale, you'd just be looking at 1 pixel going around another pixel, and it wouldn't be very exciting. So just that's a confession, but I mean wrong. So let's fly back and look at the sun. So just keep in mind that when I draw things going around each other, that they're actually very, very small, and that's because most of space is kind of empty. So if we could put all of the planets near each other, they're not this near in reality, but kind of helps you get an idea of their size. So there's the Earth. I put it in this nice place above the rings. Wouldn't that be cool? Just look out and see them. And near that is the moon. A lot of you probably can't see that, and then there's Mars. So why don't we just fly in a little bit? And you can see, oh, we've got shadows, isn't that cool? Let's fly in a bit. So this is how big the rocky planets are compared to what we call the gas giants. So the gas giants only have densities of about 2 grams per cc. The rocky planets are more like 6 grams per cc. And there's the moon there. And again, if I do it to the right scale, it would be like way away, you wouldn't go see it. Luckily, you can see it with your eyes. And the rate at which these things are rotating is all correct to scale. So if we add Jupiter to this story, Jupiter is actually bigger than Saturn. And again, we can fly around, see that the Earth is actually quite small by even our own solar system scale. Jupiter. Once we fly a while, and then that won't happen. Zoom out a little bit. So you can see that Jupiter is a little bit bigger than Saturn. Those things are a lot bigger than the Earth. But how big is the Sun? Well, it turns out the Sun is kind of large. So if we put all these near each other now, it's kind of cool. You can see the Earth and Saturn. And then if we fly above, zoom out a bit, you'll see that the Earth is kind of tiny compared to the Sun. In fact, you can fit over 1 million Earths inside the Sun, but because the Sun is not as dense as the Earth, the Sun's about 300,000 Earth masses, but you can fit over 1 million Earths in the Sun. Luckily, we're a long way from the Sun, and it's a perfect temperature to sustain life on Earth. But the Sun is not actually that big compared to some stars in our galaxy. There's about 100 billion stars in our galaxy. One of my favourites is this star called Rigel, because you can see it with your eye. It's really quite bright. And if we compare the Sun to Rigel, it looks kind of, they're similar. But actually that's just because our camera is very close to the Sun. And if we were to rotate around, you would see that Rigel is actually gigantic compared to the Sun. And the Sun's kind of pathetic. So the reason Rigel is so big is that it's a lot heavier than the Sun. It's about 20 times the mass of the Sun. And the way that stars burn hydrogen, the volume inside the star that is burning hydrogen is much, much greater in Rigel than it is in the Sun. The Sun out there is really tiny. And it actually means that Rigel is about 100,000 times more luminous. So if we were living around Rigel instead of the Sun, apart from it being really big on the sky, it would incinerate the Earth and make it an obscene temperature. Luckily, Rigel is not like the Sun. The Sun's 8 light minutes away. Rigel is 863 light years, so it's just a nice star in the night sky. But because it's burning its fuel so brightly, these stars live for only a very short time. So Rigel will blow up within about 10 million years, whereas the Sun lives for more like 10 billion years. So just remember that big stars live fast and die young. Come in. Okay? Alright. So we can see about 6,000 individual stars. There's about 10 to the 11 in our galaxy, and there's about 10 to the 11 galaxies in the universe. Depends what you call a galaxy. So, of that order. Now this is what happens if I remove everything of interest. You just get the night sky. So what I'm going to do is give you a little tour of our own galaxy. You can see the Milky Way there. There's this band of stars. It's partly obscured by dust. It would actually look much more impressive if there was no dust. But unfortunately there is dust, and dust actually comes from previous generations of stars that have blown up and put material into our galaxy. So you can see these kind of dust lanes that kind of pull. One of them is called the emu in Australia. I bet you it's not called the emu here, but it's called the ostrich. This is where the galactic centre is. And if you compare that to that beautiful image from MeerKAT, which was that big red glowing one I had earlier on, the radio waves just travel through all this dust, but the optical light gets blocked by it. And so this is actually like the galactic centre. In the middle here is the supermassive black hole, but it's very difficult for us to see it because of all these radio waves. Sorry, all these dust. Luckily the radio waves go through that, and we can actually see neutron stars all the way towards the galactic centre, although they do get scattered, which makes life a little bit hard. So we just do a little pan of the Milky Way disk, and you can see there's more stars there. That's because the Milky Way is like a big pancake of stars, and you have these sort of nice bands. That's the galactic bulge. I'm just going to stop rotating before you'll see. And I'll show you some other interesting stars. So that's actually another galaxy. And if I look carefully, these are the Magellan clouds. So they're very easy to see from South Africa. They're about 70 degrees south of the equator. And I think that one's 59. And then that little dot there is actually something called a globular cluster. It's actually about 1 million stars all orbiting each other. And all the heavy stars in a globular cluster sink to the middle. And that's where neutron stars live, and we'll learn a bit more about them later on. These galaxies are very small compared to the Milky Way. They're just called satellite galaxies. So if we take a look at some of the galaxies, this is the Andromeda galaxy. This is the nearest what I would call decent galaxy. And it's a spiral galaxy. It has these spiral arms and also has this dust. And there's lots of stars being formed in the Andromeda galaxy. Unfortunately, it's a bit hard to see from the southern hemisphere, way up north. If you zoom in with a decent enough telescope, you can actually see that it's got this dust lanes. Some of these stars are actually in our galaxy and are just in the foreground. But there's these star-forming regions, these blue areas here, where stars are being born today. This is another galaxy, which is interacting with this guy over here. And again, it's got these beautiful spiral arms. And these spiral arms occur because the galaxies actually form these bars, and they rotate differentially, and it sort of winds them up, and you end up with these beautiful spiral arms. It would be really cool to live in this galaxy because you've got to look at it this way. This is what's called an elliptical galaxy. These are very boring galaxies. These are kind of like spherical shapes or egg shapes. And because they don't compress in one direction, they're not very good at making stars. And so most of the stars here are very old and very boring. And all their exciting stars that produce pulsars died long ago. So I don't care about these galaxies. We don't want to study them. This would be a fantastic galaxy to live in. This is an interacting galaxy. It's called the Antenna Nebula sometimes. And these are two galaxies that have collided. And there's all sorts of dust and explosions and compressions happening. And this would be a really exciting galaxy to live in if you're a pulsar astronomer, because there'd be all sorts of young pulsars being formed, but it might also be a bit dangerous with lots of exploding stars around you. So we're going to move from galaxies and the stars to learning a little bit more about gravity. And Galileo was one of the first people to actually study gravity. And he did that by doing things like dropping balls off the Leaning Tower of Pisa. But he also noticed that if you took a newly invented telescope and pointed it at the heavens, and indeed you pointed it at Jupiter, you could see that it was surrounded with a slightly better projector by moons. So I'm going to turn on some trails so we can actually give your eyes a hint as to where the moons might be. And we might reorient Jupiter so it's against the galactic centre. And it might, oh, you can see the moons now, that's cool. We'll turn off the trails. Should be able to see the lack of light by the moons blocking it. The moons aren't actually that big, so I kind of cheated again, but you know how it is in astronomy. So he noticed that the innermost moons were travelling faster faster around Jupiter than the outermost moons. And he didn't realise it, but he'd actually discovered one of Kepler's laws, and that is that the planets, or things going around due to gravity, travel in ellipses, and the speed at which they travel depends on how far they are away from their centre star. So he discovered these 4 moons, and he made the remarkable deduction that if Jupiter had moons and the Earth had moons, maybe Jupiter was just like the Earth, and this displaced the Earth from the centre of the universe. So Kepler, and this is some of the few bits of maths I'm going to have in here, came up with laws about how the planets travelled around the Sun. He deduced that they travel in ellipses with the Sun focus. We won't worry too much about that. They sweep out equal area and equal time, so when they're close to the Sun they go faster than when they're further away. And he also deduced, and this was really clever, given that he was living over 400 years ago, that the time it takes to go around the star squared is proportional to their distance cubed. I was very impressed by that. And Newton then showed during the Great Plague of London, when he was banished to his hometown, he worked out the universal law of gravitation, that the force between any 2 bodies should be determined by the product of their masses divided by their separation squared. And he showed that Newton's laws were just a simple consequence of this, and he came up with that the orbital period, and I have t here, it's now p, is proportional with a to the 3 halves. So if we actually look at Mercury and how it travels around the Sun, it actually traces out this elliptical shape. Just fly overhead more easily seen. So you can see it's got this elliptical shape. It travels faster when it's near the Sun than it does when it's a long way from the Sun. And these are just Kepler's laws in action. Einstein started modifying Newton's laws of gravity, and he did so by doing these amazing thought experiments. So if Einstein was to fall from the sky, he would travel faster by about 10 meters per second for every second he was falling. So after 5 seconds, he would be going 50 meters a second. After 1 second, he'd only be going 10 meters per second. And this acceleration due to gravity was the kind of thing that Einstein used to dream about. And if he could fall due to gravity, maybe light could as well. So he undertook these remarkable thought experiments, and that led him to his general theory of relativity, which is really, really hard to understand, even somebody who studied it like me. But he deduced that if you were accelerating due to the gravitational force, or accelerating due to the fact that you were accelerating in outer space, that you would feel exactly the same. And he deduced that if you're an atom and you felt a force due to gravity due to a world being underneath you, or you felt a force due to the fact that you're accelerating, you wouldn't be able to tell the difference. And this led to his equivalence principle, which is the foundation of his theory. He also deduced that you couldn't actually tell if you were falling in a gravitational field or you weren't falling at all. So if you're in an elevator and it had no windows, you would just feel like you were floating. Or if you were in an elevator that was in a gravitational field, you would have exactly the same force on you, which would be 0. But you would actually be accelerating towards the Earth. And so this equivalence principle was the mathematical foundation, or the assumption behind the mathematics of his general theory of relativity. And although he deduced this general theory of relativity, when Einstein was alive, there was very few ways you could test it. He also thought that if you can't tell whether you're falling or not, that light should bend around bodies. So due to the gravity, the space-time should be distorted in such a way that the light beam doesn't go straight, it actually bends. And he also worked out that time should tick more slowly strong gravitational field than in outer space. So if you have two clocks and put one near a body and you have one a long way from the body, this one's going to tick faster than this one. And so all of this seemed pretty magical back in the early 1900s. He also deduced that if you had a measuring rod and you stuck it in a gravitational field, it would shrink. And if you put it in outer space, it would expand. But the amount it shrinks is so tiny that he thought it was just a sort of a useless conjecture. He also deduced that there should be something called a black hole, and the black hole would exist if it obeyed this formula here. So the radius of the object, if it was ever smaller than twice Newton's gravitational constant, it was nice of him to leave Newton's constant in his theory, times the mass of the object divided by the speed of light squared, it would become a black hole, and light wouldn't be able to escape. The only problem was, to turn the Earth into a black hole, you would have to shrink it to 1 centimetre radius, which is really, really hard. In fact, even with modern physics, we can't even take a litre of water and shrink it to a 1 centimetre radius, let alone the whole planet. If you're the Sun, because this has a linear relation and volume has a cubic relation, the Sun would be a black hole if you could shrink it to 3 kilometres in radius. That's a little bit more feasible because it's 3,000 cubed times as much volume for only 300,000 times as much mass. Nevertheless, again, he thought maybe black holes were just a theoretical conjecture with no actual physical meaning. He also realised that if gravity was a bit like electromagnetism is charged particles and light, that maybe whenever two masses went past each other, they should give off something called a gravitational wave. And a gravitational wave would stretch and squeeze space, or stretch it this way while it's stretching it that way and pulling it in, and then, so if I was a gravitational wave, I would be kind of doing this if I propagate it along. And he worked out the amplitude of the gravitational wave, how much would it shrink and stretch stuff. And he realised that if two black holes coalesced a million light years away, it would cause a 4-kilometre measuring rod to shrink by 1/10,000th of the width of a proton. And that was probably completely immeasurable and nothing more than a theoretical conjecture. And he actually made a terrible mistake one day, and he woke up and thought, oh my God, there are no gravitational waves. And he wrote a paper about it and submitted it to a journal. And it went to a referee who was actually smarter than Einstein. And he said, no, Einstein, you're actually wrong. There will be gravitational waves. And he rejected the paper. And Einstein got so cross, he never submitted another paper to that journal ever again, even though he was wrong. And there were actual gravitational waves that existed. But he didn't understand his own mathematics. And he actually explained to people that he wasn't actually that good at maths, but he was really good at thinking up problems to work on. I suspect he was a lot better than your average person at maths. So there are some classic tests of general relativity. One of them is that light should bend when it goes past the body. And the biggest body we knew of in our solar system was the Sun. The only problem is if you try and see light bending around the Sun, you have to stare into the Sun. So that's really bad and very difficult. But what you can do is you can wait until there's a total solar eclipse, which happens every few years, and you can send people with telescopes on expeditions to photograph the pictures of the Sun when it's being eclipsed, and look at the stars behind it, and their positions should change if light is bending. And so a guy called Arthur Eddington did that, and he showed that the light actually did change. I think it's by about an arc second or something. It's 1/3600th of a degree. It's actually given by this formula here. Somebody could work that. B is the impact parameter so it would be a solar radius. And so the light bends, but this is again greatly exaggerated to help you understand it. So that was a test of general relativity, and it kind of worked, but the data was all sort of noisy and points went everywhere, and some people wondered if Eddington had fudged his data, but it was repeated many times and shown to be correct. The other test of general relativity was that he showed that because gravity only travels at the speed of light, the elliptical orbits of Kepler should actually change their orientation very, very slightly. And Einstein predicted that general relativity says that the elliptical orbit of Mercury should change by 43 arc seconds every 100 years, which doesn't sound like very much. But luckily, Mercury is very close to us, and this anomalous change in the elliptical plane of, not the elliptical plane, the elliptical orientation of the ellipse that Mercury undertakes is such that this was known about when Einstein's theory came along, and he said, aha, I've explained it. And so if we put on the trail of Mercury, we fly above it, this point of closest approach, every 100 years will move by 43 divided by 36 hundredths of a degree, which is not very much, but it has been confirmed experimentally. The other thing that you could do, and this was after Einstein was dead, is that you could take an atomic clock and you could stick it in an aeroplane. So they actually bought 2 seats on the aeroplane, they stuck an atomic clock, it flew about 10 kilometers above the Earth, and they measured how fast it ticked by taking it back to another atomic clock that was on the ground, and they compared the 2 clocks, and the one that had gone up in the aeroplane, had ticked a bit faster than the one that had stayed on the ground. And in fact, the GPS satellite system that we use for modern navigation takes this what's called general relativistic faster ticking into account. Otherwise all the clocks wouldn't be synchronized properly and would all get lost. And your jumbo jet would run into the ground. So in terms of gravitational wave detection, that's these little feeble waves that 2 masses, whenever they go past each other, give off. Einstein said, forget it. It's not going to happen. But he didn't realise that lasers were going to be invented, or that radio astronomy was going to come along and save the day. So if we just review the strength of gravity in our own Earth, the speed of the equator is about 462 meters a second. Satellites that are in low Earth orbit have to travel about 7 kilometers per second, otherwise they fall into the Earth. But they actually fall at the exact rate which keeps them in orbit. And you can escape the Earth if you can go 11 kilometers per second. But these numbers are actually all pretty small compared to the speed of light. So in Einstein's theory, interesting things start happening as you approach the speed of light. And the speed of light is not 11 kilometers per second, it's 300,000 kilometers per second. So luckily, for pulsar astronomers everywhere, Jocelyn Bell, our hero, came along in 1967, and she used to use a radio telescope. It was the first one to have what we call high time resolution, and it was because they were studying twinkling quasars, which are supermassive black holes that give off a lot of radio waves and are very compact. And when they were in the ecliptic plane of the solar system, they used to twinkle, and her job was to study the twinkling stars. And luckily for her, she discovered pulsars. And she was very astute and noticed that there was this bit of what she called scruff. This is a chart recorder. They used to have these little pens, and you'd fill them up with ink, and then they would measure the amplitude of radio waves, and they would rise or fall as a bright source went overhead. And so she noticed that at this particular time, the chart recorder was going up and down for some reason. And then a few minutes later, it was probably, 10 minutes later, it went up and down again, but this was actually due to interference. So if you do something like start a car engine, it causes radio waves to be emitted, and your radio telescope picks them up thinking they're extraterrestrial. And so this is actually a real plot of what happened when they thought, let's investigate this in a bit more detail. So they used up a huge amount of paper, and they had higher time resolution, and you can see there's these little valleys here. That's because up on this graph is down. And this is actually radio waves hitting the telescope quasi-regularly every 1.33 seconds. So this is only about 20 seconds of time. So you can imagine how much paper she was going through. must have caused the incident in the Cambridge Observatory. But this was the first ever observation of pulsars, and it was back in 1967. I was born, but I don't remember it. I was only 4 and a half at the time. And this was a bit of a sensation. It was published in the journal Nature, and about 8 years later, the supervisor won the Nobel Prize for the discovery. I don't think a lot of people had any trouble with him kind of coding it, but she was that out, which was that sign of the times. So we now believe that pulsars occur because radio waves sweep through the universe, powered by these things called neutron stars. So the neutron stars, the slowest spin once every few minutes. The fastest one spins 700 times a second. So it's something 20 kilometers across, and actually has a complete rotation 700 times every second. And these radio waves travel through the universe. They hit our radio telescope. They induce a voltage. We amplify that voltage. We digitize it. We send it to the computer, kindly donated by Swinburne University, and we can study it. They have enormous magnetic field strengths. A magnet on your fridge is about 100 Gauss. These are up to 10 to 14 Gauss. They weigh about 500,000 Earth masses. There's about 3,500 known, and almost all of them live in our galaxy. And they're only about 3 times bigger than a black hole would be. So they're very rapidly rotating when they're first born. This is because the core of the star is already rotating, and when it collapses, it's a bit like a boom, that's scary. It gives off a big loud noise. When it collapses, it causes it to conservation of angular momentum, causes it to spin very rapidly. And so neutron stars, when they're first born, spin about 50 times a second. This is what one looks like up close. They have these very intense magnetic fields. And charged particles travel along magnetic field lines, which is why I've drawn them here. We call this thing the magnetosphere, and we think charged particles roar along these magnetic field lines. They cause pair production of positrons and electrons, which forms these cascades, and you get radio waves traveling along in a beam. And the density of these stars is so high that it's about 1 billion tons per cubic centimetre. And that's because unlike normal matter, they don't have big electron crowds around their subatomic particles. The neutrons are right together, almost kissing. So the acceleration on the neutron star, instead of being g 9.8 meters per second squared, it's actually 200 billion g. So you wouldn't want to try and stand up on one of these things. You could just crush the smithereen. So they have amazing power when they're first born, and this is because magnets don't actually like to spin. They give off something called magnetic dipole radiation. And they also have an enormous voltage. So this would certainly fry the South African power grid and lead to the mother of all load shedding. But these are a giant particle accelerator. And if you're in the right position, this beam of radio waves hits your telescope and causes you to receive a pulse, just like Jocelyn Bell did back in 1967. So if I orientate this thing just right, we'll see that you get this flash of radio waves once per rotation period. If it has a complicated enough magnetic field state, sometimes you get 2 pulses per pulse period, or sometimes really complicated pulses. But we actually use the fact that they're rotating very regularly to work out how long the light has travelled in order to reach us. And if the neutron star is going around another object, the time delay, because it's travelling, means we can map their orbits and do tests of Einstein's theory of relativity. So this is a picture of Jocelyn Bell shortly after the discovery was announced. The radio waves actually don't travel at the speed of light. They travel very, very slightly smaller. And that's because the radio waves come across electrons in our galaxy. And you only actually travel at the speed of light in a vacuum. Because the light is a changing electric and magnetic field, every time it sees an electron, it slows down. and it actually leads to the high frequency radio waves hitting our telescope earlier than the low frequency ones. And you can actually use this to determine how many electrons are in our galaxy. And you can also determine how many electrons are in the universe if you can find something that gives off radio waves in the distant universe. And while we were looking for pulsars in our galaxy, we stumbled across these strange things called fast radio bursts that only give off a radio burst once, and you can use that to help weigh the universe. So the velocities on neutron stars are very different from the velocities on Earth. They spin around about 2,000 kilometers every second. If you were in orbit around a neutron star, you would have to go about 141,000 kilometers per second. And to escape a neutron star, you have to go about 2/3 of the velocity of light. So they're very relativistic objects. Unfortunately, Einstein didn't live to see them being discovered. So, in the same way that Mercury goes around the Sun every 88 days, and its ellipse is precessing at 43 arcseconds a century, imagine what you can do if you had two neutron stars going around each other, because they would weigh more than 1 million times as much as Mercury does. And so, in 1974, a student, again a pulsar PhD student, for those of you thinking about doing a PhD in pulsars, there's Nobel Prizes galore to be won. A guy called Russell Holtz discovered something called the binary pulsar. It was spinning every 59 milliseconds. But it was the first ever neutron star to be going around another star. And not only did it go around another star, instead of taking a year like the Earth goes around the Sun, it actually went around the star not every few seconds like in this animation, but it was actually every 7 3/4 hours. But since this lecture is only an hour long, I didn't think we'd do it in real time. So you have this neutron star, it's spinning at every 59 milliseconds. Every 8 hours it goes around its friend. And the degree at which the ellipse is changing its orientation is 4.2 degrees a year. So this is what the elliptical orbit looks like of the binary pulsar. It's got what's called an orbital eccentricity of 0.617. So it's quite an egg-shaped orbit. It travels faster when it's near its friend than when it's a long way away. And the plane of this ellipse is changing by 4.2 degrees every year. So not 43 arcseconds a century. It would do 420 degrees a century. And in fact, this thing's actually been known about since 1974. And so the orbit has changed by almost 180 degrees. And you can determine the masses of this system. One of the stars is 1.44 times the mass of the Sun, the other is 1.38. And because of that, you can take Einstein's general theory of relativity and you say, how much energy should be coming off in gravitational waves if these two systems are going around each other? And what Joe Taylor realized was that if you just timed when the pulses came from this thing for about 20 years, you would actually go see the orbit shrinking because it's giving off gravitational waves. And unfortunately, the amount it shrinks is only 3.1 millimeters in orbit. And this thing is 25,000 light years away. And so you might think measuring 3 millimeters in orbit at 25,000 light years is very tough. But luckily, it shrinks by 3 millimeters in the first orbit, and then after the second orbit, it's shrunk by 6 millimeters, and the third is 9. And the amount of time it takes to go around its orbit keeps getting less and less. And it actually is measured in several seconds after a decade or so. So Einstein said these two neutron stars should be giving off these gravitational waves. You can work out how much energy that's taking from the orbit. And I just settled this, so I won't say it again. But basically this adds up to several tens of seconds over the course of 30 years or so. And so at about this point here, the Nobel Prize Committee decided they would give Joe Taylor and Russell Holtz the Nobel Prize for timing this pulsar for many, many years at the Great Arecibo Observatory. So what this graph is, it shows how early should you get back to the point of closest approach as a function of year. And if there were no gravitational waves, all these experimental points should lie along this line here. But this is the Einsteinian prediction of when these two stars should get back to their point of closest approach. And it's just a beautiful confirmation of Einstein's theory. And so because these things were were shrinking, you could predict that in 300 million years they would actually destroy each other. And then scientists worked out, well, if you just build something that could monitor the nearest million galaxies for neutron stars merging, and build something called LIGO, you might be able to detect gravitational waves from merging neutron stars. So Joe Taylor won the Nobel Prize in 1993. I still think it's because it was 4 years after he marked my PhD, but Nobel Committee thinks otherwise. So they went to Congress and they said, if you just gave us $1 billion, we could build 2 4-kilometre long vacuum tubes. We could fire a laser beam down on them, sort of like James Bond style one. But that light would bounce off the mirrors and come back, and if gravitational waves went through the Earth, the mirrors would shrink by about 1/10,000th of the width of a proton. And if we put a megawatt of laser power in here, we could measure that. And Congress said, sure. And so they built it, and then lo and behold, in 2014, lasers went through this actual tunnel, and they bounced back, and 2 black holes, about 1 billion light years away, destroyed each other. The whole thing shook by 10/10,000th of a proton. You wouldn't really measure it unless you had a laser beam with a megawatt of power in the cavity, and they detected gravitational waves. And then only 2 years later, they actually saw 2 neutron stars merge, and this is the power in the frequency of the gravitational wave versus time. And this streak here is the signal that the experimentalists measured when the 2 neutron stars merged. And the 2 neutron stars were going around each other 1,000 times a second when they tore each other apart. And then 1.5 seconds later, there was a burst of gamma rays hit the ionosphere of the Earth and were detected by the Fermi satellite. And then they looked in the sky based on the where the gamma rays were and the neutron star merger signal was, and there was a brand new star there that lasted about a week, and then about a month later it lit up. Well, it didn't light up the sky, it was this pathetically small radio source in the sky, and that was the afterglow of the 2 neutron stars having destroyed each other. So let's get on to MeerKAT, the last part of the talk. So I think it's the best radio telescope in the world for pulsars, and it's why my team and I are here to use it. So it has these 64 dishes. The pulses come from the heavens, they bounce off all these bits of metal. It has about 4 times the collecting area of the Parkes telescope in Australia, and it's just a fantastic place to observe pulsars. And so when we got interested in this telescope, we had to write a proposal about all the things we would like to do if we could get time on it. And so we built this international collaboration, and we were going to explore the curvature of space and time. We were going to explore extreme gravity around 2 neutron stars called the double pulsar. We were going to test general relativity. We were going to see if we could see the eclipse of the pulsar, and also whether we could see the influence of supermassive black holes on lots of millisecond pulsars floating around our galaxy in a sort of galaxy-scale gravitational wave detector. So this is one of my favourite pulsars, 1909-3744. It spins about 300 times a second. It has a white dwarf companion. And when the light from the neutron star goes past the white dwarf, Einstein said that the measuring rods should shrink and should take longer for the radio waves to reach our telescope than if the white dwarf had no effect on the propagation. So if we orient the system so that edge on, then white dwarf goes in front of the pulsar, and the radio waves, as they go past the white dwarf, it's not quite big enough to block the neutron star. the signal should take longer to reach us than if there was no general relativistic effect. And so we can plot the arrival time of the pulse as a function of the orbital phase of the system. And so we did that with MeerKAT, and Ryan Shannon produced this figure for me, and he's sitting in the audience. Well done, Ryan. And this is the delay in microseconds, not very big, predicted by Einstein should have this shape. And then these points are our experimental data. And you can see it's just a beautiful confirmation of Einstein's theory. And indeed, the light does take about 12 microseconds longer to reach us than it would if relativity was wrong. And these are the residuals of the experimental points take Einstein's curve. And they're beautiful. And I'm looking forward to seeing the next version, Matt. Your data. So next, we're going to look at something called the double pulsar. J equals 737 minus 3039 A and B to his friends. One of the pulsars spins at 22.7 milliseconds. That's about 33 times a second. The other one only spins about once every 2.7 seconds. I think we can do that. This pulsar here is old and dying. This one here got accreted matter and is spinning very quickly. They go around each other 10 times a day. So the two neutron stars go around each other 10 times a day. And it's the best way to test relativity in the whole universe with a radio telescope. And so you can see not only space-time then, but you can also measure all of those relativistic effects that Russell Holtz and Joe Taylor received Nobel Prizes for, because it's so much more relativistic than the original one. The orbital period is less than a third of what the original binary pulsar was. And so we measured all of these parameters. This is the PhD thesis of Dr. Hu, H-U, Hu Chen Hu, I think her name is. So we measured the orbital period, and it's 0.102, 251, 559, 2792, with an error of 29 in this last place. So we've measured the orbital period amazingly accurately. The diameter of the orbit is measured in light seconds. 1.415028 299 with an error of 88 in the last place. And so all of these amazingly accurate measurements have meant we can determine quantities in the system much more accurately than ever before. So the rate of change of the elliptical orientation is 16.899321 degrees a year. The orbit is shrinking by 1.247920 by 10 to the minus 12 seconds per second. And we can also measure the time delay due to what's called Shapiro delay, that's the extra measuring rods. And this enables us to determine the mass of the first pulsar. It's 1.338186. So we know it to better than the mass of the Earth. And its companion with this, and the total sum of the masses is that. And we can use all this to test relativity. And we can also see evidence of light bending. So when the pulses are coming from the neutron star, the radiant, when it goes past its companion star, the light bends. And we actually see the neutron star in a slightly different rotation phase than we would otherwise do it. And this is the prediction of the shape of the extra delay. This is only 2 microseconds, pretty cool. And this was a very unique test of relativity, again, done by MeerKAT. And finally, in this system, one neutron star goes past the other neutron star, and it has this sort of strange disk that blocks light from the star. And twice per rotation period, I don't know if you can see it very well, but there's a quasi-disk here, and it lets light go through, and then it blocks light, and then half a rotation of this slow pulsar later, we start to see the radio waves. And so we can examine the magnetosphere of one neutron star by looking at the other one. And when we do that, we can actually see that the intensity of the neutron star goes from normal to having these absorption features. And the gap between these absorption features is exactly half the rotation period of the slow neutron star as it goes past. And then this is the prediction of Einstein as to how space-time should curve as the light travels from one neutron star to us, and again it follows Einstein's prediction almost perfectly. O437 is one of my favourite pulsars. It's the brightest pulsar in the sky that rotates at millisecond periods. It was discovered by Duncan Lorimer back in 1992, and I still remember coming into the office and he just had these two plots and he marched towards me with them, and they had these dark stripes on them showing that we've discovered this incredibly bright pulsar. It has a circular orbit, and it's got a distance of 156 parsecs. And Daniel Reardon, who's sitting in the audience, has been examining how the energy from this pulsar collides with the sort of atmosphere, if you like, of our galaxy. And it pushes it away and forms what's called a bow shock. And so if you take an image in hydrogen alpha, you can actually see this is the companion of the pulsar. We can't see the pulsar. It's what's called the white dwarf. It's an inverted image. So it's actually shining, and it's got this sort of bow shock, a bit like a ship going through the ocean, but instead this is a neutron star traveling through our galaxy. And so what Daniel did was he measured how this star is twinkling, how the pulsar is twinkling, and every time it comes past a sheet of material, you get one of these strange parabolic arcs. And you can use the fact that these parabolic arcs change throughout the orbital period to measure how far it is to the sheets. And it turns out one of those arcs corresponds to the front of the bow shock, and another one to the middle, and another one to the what's called the termination shock. And so this is in a paper that we're about to submit, right, Daniel? I said that about a year ago. But now he's got the data and it's all beautiful. And then finally, Matt Bailes, for his PhD, with Ryan as his supervisor, has been trying to see whether all of the millisecond pulsars that hang out in the universe, or in our galaxy, are being perturbed by supermassive black hole binaries that are making the whole space-time between Earth, which is about to disappear, and these pulsars change their effective distance. So if there are supermassive black holes, the time delay from these neutron stars should change by an order of 100 nanoseconds or so. And if we can plot the time delays of closely separated objects compared to objects 90 degrees apart, we should get something called the Hellings and Downs curve. And Matt's been good enough, sorry, that was Ryan, to do the simulation of what this would look like if you had data of similar quality to MeerKAT. And it should, points that are very close should be highly correlated, points that are 90 degrees apart should be different. And so we're hoping to produce a plot just like this one and show that there are gravitational waves and supermassive black holes in the universe. So just to conclude, MeerKAT and pulsars are an awesome combination, and we're very grateful to the South African people for building such a wonderful instrument and allowing us access to it. If you'd like to get involved in this kind of science, come to a workshop here at Potch and learn more about the pulsars. And thanks everybody for your nice hospitality, and I'll take any questions.
So can you please elaborate and turn around the milestone?
Increase my signal to noise ratio.
No, like I missed something. Like you mentioned the fact that that pulsar are projecting materials toward hours, right? Which means hours are emissions in the hemisphere, right? And if that thing happens like that, it's a body shock. However, evidence has stated that it may not initially be a body shock. And it change to be a dialogue, depending on which paper you go with, right?
So the neutron star signals, by the time they arrive at the solar system, are awarded 10 to the minus 29 watts per square meter per hertz. And so they have almost no impact on the sun or our Earth. But radio waves are such an efficient transmitter of information, we can still see that the rapid pulsars don't actually change the amount of, or virtually anything on Earth. However, if two neutron stars collide, they give off a gamma ray burst, and that can do things like ionize the ionosphere, and that we've seen that.
More questions?
You got another question?
Just last one. You lost me some part. Like you mentioned that you can't record stuff where there's an invisible disk. Do you have any suggestion of why you can't do such? Because you say that on one half you can record this invisible disk and the other half you can. Do you have any theories on what will cause it?
I think you might be referring to the double pulsar, which is blocking the radiation. Yeah, so I think that was a bit of a surprise when people noticed that if you looked at the double pulsar, it sort of half disappeared whenever the neutron stars went past each other. And I think it was actually Fernando Camillo who just discovered that. He now works at Soraya. And I was in the control room with him when he discovered that. He went, hey, look at this. The double pulsar is like being eclipsed. What's going on? And when they studied it with a higher time resolution, you could see that once every half of the spin period of the slow pulsar was blocked. And so people postulated that there was some disk of ionized radiation, and radio waves have trouble getting past. So radio waves don't like electrons. If you have high densities of them, they can scatter the light so that you can no longer see it. So my suspicion is that there's some sort of plasma cloud which has some sort of toroidal shape, and it's just the right geometry that when it spins, it blocks the radiation. But I'm not really a theorist. I'm just going to take the data and compare it with theories of gravity. They're much easier to understand. We've got one up here.
Thanks, Mark, for the wonderful talk. My question is, with regards to the pulsars and binary systems, how does massive stars in the binary system we have pulsars, how does it impact the arrival time for pulsars?
I think I've got about 8% of that, like the eclipsing double pulsar. So you're asking about binary systems and how...
In the case of binary system, where the counterpart, the companion is a very massive star, how does it impact the arrival time of the pulse?
Good question. So, depending on the mass of the star and its stage of life, if you have a really massive star, say 20 times the mass of the Sun, it actually has a very strong called solar wind. So our Sun gives off about 10 to the minus 14 solar masses a year in solar wind, and that's what's called the aurora. In a 20 solar mass star, you can have winds that can be 10 to the minus 5 solar masses a year. And when a neutron star goes too near a star like that, it actually blocks the radio waves and you get an eclipse. And there's a famous system, 1259-63, which goes around, it's a neutron star that's very young, but it's going around its companion star every 3.5 years. And for about 3 or 4 months a year, we actually lose sight of it when it goes near the companion star. And it hits this disk of material. It actually lights up in radio waves that are not pulsed. And it also gives off TeV gamma rays as the magnetosphere of the pulsar interacts with the disk of material, and then it becomes visible again. And we've actually been monitoring that with MeerKAT, and we've seen it disappear and come back again.
One last question.
What time is dinner?
Sorry, this is just rhetorical. Have there ever been a case where pulsars separate matter from their companion star?
Yes. So there are things called X-ray pulsars, and they're neutron stars that are so close to their companion that they're either accreting the solar wind from the companion, or they're having material dumped on the surface of them. And they become very bright in X-rays, and they actually become, I think it's about 10 to the 7 times brighter in X-rays than the sun is. We call them high-mass X-ray binaries, and those sources are giving off so much energy that the energy density on the surface of the neutron star is 10 to the 5 nuclear wars per meter squared per second. Which makes them easier to see. But you wouldn't want to live there.
Can I quickly ask you to just say a few words about MeerKAT and 1,000 plus projects?
Yeah, so pulsar astronomers tend to be greedy and try and get as much time on telescopes as they can. And so one of my good friends, I hope you're not listening, Simon Johnston, decided that they would look at 1,000 pulsars with MeerKAT. And because MeerKAT is so big and sensitive, they actually break it into 2 halves. And they monitor 1,000 pulsars about once a month. And they're studying how they rotate and whether or not their rotations are regular or not. And they've seen earthquakes on some of the neutron stars, but they're also seeing interesting effects where the torque on the neutron star is changing with time, and that's related to the Potchefstroom. And all that data is public from day one, so you won't look at pulsars.org.au.
Okay, I think it's that is one more.
Actually, I have very light questions, simple question. You showed the movies all over the top, so I want to just know which software it was made.
Which software?
Yeah.
So it's in something called OzView, which is custom software developed by my Centre of Excellence. And it enables you to make random binaries. So you can go to a slide and click here, and you can say, I want to add a black hole. And you can scroll down to a black hole with text, and you can stick it in the scene. And if I give it a position of y equals 10, and I'll give it some incredibly huge mass, like 1,000, and save the changes, then I can, well, now I have to find a slide. It's not that easy. Oh, there we go. And then a black hole destroys the Earth. I can replay that.